Last video, I showed you that the address is just an abstraction. It's a fingerprint of a public key, and it's sitting right here inside the locking script as a 20 byte hash. I want to talk a little bit about a transaction. When you write it, has inputs and outputs. And there can be one or more of each. So the locking script from the last video was associated with one output. And in this video, what we're going to do is show the unlocking script that you need for spending it. So let's get rid of this. And just as a reminder, this is the lock. And we're now going to look at the unlock. And the unlock, in the case of the P2PKH, that's pay to public key hash, that's one script type of many in the BSV ecosystem. That unlocking script is very simple, and it is simply signature, let's just call it SIG, and public key. That's your whole unlock script. And as you can see, there's no opcodes on this. I mean, technically there's a little data push opcode, but I'm not going to complicate it with that. And if you look over here on the right, you'll see that I've created a little a table that walks us through the scripting mechanics for this unlock. So when the transaction is verified by the miners, by the verification engine, that engine takes your unlock script and it adds the lock script after it. So we've got SIG, pubKey, we've got, I'll just make a copy of this. So to unlock, the verification engine puts all this together. And then if you look over on the right, we're going to do some operations. So the first thing that we're going to do is we are going to drop in the signature, and we're going to drop in the public key. So look over on the right, and you see in the second row here, we've now on the stack got a SIG and a public key. So notice in the dark pink, they represent data, okay? And in the stack, all that goes on the stack is the data. The green are the opcodes. And so the next one in line is op dupe, and then op hash 160. You can follow along and look on the card, and you'll see that's we're staying in order here. And then the next one is data again. Okay, so I'm going to put that in pink, and it is that 20 byte hash that represents my public key that I have control of. So my output, my UTXO. Next in line is another opcode. So let's put it in green. So op equal verify. It's an opcode. And now we have another opcode, and that is op check sig. So there's our whole, so this is our recipe. It's like we're going to cook something, and we're going to cook a transaction, and this is the recipe for cooking it. And the stack is how we take the recipe and we take the opcodes and do things to the data in the stack. So the first thing that we're going to do is we're going to look at the stack. So let's look on the right, and we see, and you can follow along what I'm going to do. This is the stack here. We're going to pop the sig and the public key onto the stack, because the only thing that goes on the stack is data elements. And what's next in our recipe? Oh, it's opdupe. So what opdupe does is it looks over onto the stack and it looks at what's at the top. And I see I put these in the wrong order, so I am going to repair that. So the opdupe looks over at the top of the stack and it duplicates it. So let's move that down, and we are going to duplicate this public key. All right, so now we have done what we need for the first three things in the recipe. Now we have another operator. We have another operator, an opcode, and it's ophash 160. So what this ophash 160 is doing is there's two hashing algorithms in this opcode, and it is doing that to what it sees on the top of the stack. So it's taking this public key that we just made a copy of, and it's doing those two hashing algorithms to it. So we're going to take that off because we've just done those two hashing algorithms, and we are going to put a 20 byte hash that we just did. So now we just have a hash here at the top of the stack. Okay, so we will check that off. We've done that. And now what do we see here? We have data. Oh my, we have data in our recipe. So we are going to add that data to the top of the stack because it's the next in the recipe. All right. So let's check that off. And what's next in our recipe? Oh, another opcode. So let's do this. And it's looking at the top of the stack. Op equal verify. And what this opcode is doing is it's looking at the top two items and it's verifying that they're equal. If they're equal, both of these things get thrown off the stack Well, let me just say this. If it wasn't equal, we would get a big red X, and the miners would throw that out, okay? We are pretending that they are equal. So then what happens is these go away. This is done. And what do we have left at the top of the stack? We have the pubKey and the sig. And so now, and what do we have left in the recipe? We have we have op check sig. So op check sig is now looking at the top of the stack, and it is checking to make sure that this signature that you've provided here in your unlock script, we're making sure that it is a valid signature over your transaction that is spending what was locked. And so there's more to the mechanics here, but this is roughly put what's happening. So this opcode is checking to make sure that the data that you provided, that your signature actually was valid, the one that you handed over to the miners to unlock your UTXO, your lock script for your output that you control. And so then if, is it true? And if it's a yes, then it's valid and it is now an empty stack and it's allowed to be put into a block. And that is the end. So to review, the address was only ever the label that carried the fingerprint to whoever paid me. Spending is where the real key finally steps out and proves itself. The script mechanics, I think, is important to understand the basics for. And then once you have it down in your mind, the SDKs and such, and some other tools that engineers have built will make it so that you won't need to understand this going forward as a developer.
Got a curve in the game, laid out clean with the point named G and a math machine.